I want to look at two more examples so we can see other situations where we can look at the limit of functions that can be simplified. So let's just jump in. Here, we'll look at the limit as h approaches 0 of 9 minus the quantity 3 plus h squared all over h. This is another situation where we have a rational function. It's not quite simplified. We've got that binomial squared up in the numerator, but it will be a rational function. And we can't use the direct substitution property because that would end up giving us a 0 in the denominator. But what we can do is we can simplify that numerator and see if there's anything that we might be able to cancel. So let's go ahead and do that. If we take 3 plus h quantity and square it, that is going to be 9 plus 6h plus h squared. You can go ahead and FOIL that out if you need to. And then we can distribute that subtraction in the numerator. So let's do that and see what it gives us. That gives us 9 minus 9 plus 6h plus h squared all over h. And you probably are already noticing 9 minus 9 is 0. So that just goes away. And we can write this as the limit as h approaches 0 of 6h plus h squared all over h. And we can factor out an h in the numerator and denominator. I'm going to move over to the right here just so we've got room for another problem below. So this is the limit as h approaches 0 of h times 6 plus h all over h. And then we can go ahead and cancel out those h's. And the reasoning is that we're looking at the limit as h approaches 0. So we're looking at values of h near 0, but not equal to 0. So we know here explicitly h is not equal to 0. So when we cancel out the h in the top and bottom, we're dividing by something that's non-zero, which we're allowed to do. And then this just becomes the limit as h approaches 0 of 6 plus h, at which point we can use the direct substitution property. That gives us 6 plus 0, which is just equal to 6. So that's that limit. Let's do one more. I want to show you a little bit of a variety of some of the different problems we can look at. Here we have the limit as t approaches 0 of the square root of t squared plus 9 minus 3 all over t. Now this is a more complicated one. This one is not a rational function. We've got that square root in the numerator. If we, even so, tried to plug in t equals 0, we would still end up with 0 in the denominator. So even if we could do that, we could try and move the limit into the numerator and denominator and move the limit inside the square root and go through all of that. It still wouldn't work because we'd have a 0 in the denominator. So we need to do something to get rid of that. And there is a neat trick that we can use here when we've got something that looks kind of like a rational function, but there's a square root somewhere. We can multiply the numerator and denominator by kind of the conjugate of this. Instead of that square root minus 3, we can multiply by that square root plus 3. So the square root of t squared plus 9 plus 3 in both the numerator and the denominator. And it's probably not at all clear how this is going to help, but you'll see in just a moment. In the numerator, we've got a difference times a sum. And remember, that's basically the difference of squares. If we have a difference, a minus b, times a sum, a plus b, That's equal to a squared minus b squared. So what we can do is we can use that formula to multiply those out, and we end up with that first thing squared. So that's going to be the square root of t squared plus 9 squared. And then minus the other thing squared. So that'll be 3 squared. And then that'll all be over t times the square root of t squared plus 9 plus 3. We're not going to distribute that t in because we're going to have some nice cancellations in a little bit, I believe. So let's see what's going on in the numerator. If we look at that numerator, the first part, when you take the square root of something and then square it, you just end up with the original value. So that's just going to be t squared plus 9. And then minus 3 squared is the same thing as minus 9, all over that same denominator that I'm just going to rewrite here. And then you probably already notice 9 minus 9 is 0 in the numerator, so those go away. And oops, I made one of the big no-no mistakes here. I forgot to write the limit because we're looking at a limit here and we need that limit written for each step. So I'm going to go ahead and erase that equal sign and move it over so I can make room. I actually was going to mention in the previous problem, remember to write the limit each time, and then I happened to forget once myself. So please, it's very important. If you do not write the limit in each step, what you've written is mathematically incorrect because the limit of something is not just equal to that expression. We need to have the limit written each time. So now that we've fixed that mistake, we can move forward. And then this is just going to be t squared over t times that quantity. And then at this point, you're probably noticing that we can cancel a factor of t in the numerator and the denominator. The denominator has a factor of t, and the numerator has 2 of them. So if we cancel out one of them, instead of a t squared, we're just left with t. And so this is going to be the limit as t approaches 0 of t over the square root of t squared plus 9 plus 3. And we can't use direct substitution yet because that doesn't work when there is a radical. But we can do a few things, and I'm going to do a couple of them at once. Remember, the limit of a quotient is equal to the quotient of the limits. So we could take this limit and move it into the numerator and the denominator. And then the limit of a sum is equal to the sum of the limits. So we can put the limit of this plus the limit of that. And then the limit of the square root of something is equal to the square root of the limit of that thing. So we can pull the limit inside. And effectively, once we've done that, this is equal to the limit as t approaches 0 of t over the square root of the limit as t approaches 0 of t squared plus 9, and then plus the limit as t approaches 0 of 3. And once we're at this point, we can use direct substitution on all of those limits because those are all polynomials. And so that's going to give us 0 in the numerator when we plug that in for t. And then under the square root, it's going to be the square root of 0 squared plus 9 and then plus 3. So it's going to be 0 over the square root of 9 plus 3, which is 0 over 3 plus 3, which is 0 over 6, which is 0 in the end. We couldn't just stop when the numerator was 0, because we have to make sure the denominator is not also 0. If it's 0 over 0, that's undefined, and we've got to do a little bit more work in that case to find the limit. But once we see that it's 0 divided by 6, we know that it ends up equaling 0, And that is the value of our limit here. And I want to say two more things really quick, one about this particular problem and one about these in general. In this particular problem, if we go back to the beginning, remember that the trick that we used here when there was a difference involving a radical was multiplying by the sum involving that radical. And the reason for that is when we've got a difference times a sum, that gives us a difference of squares. And having that difference of squares allows us to get rid of the square root. And then we've got something that is a lot simpler and we can work with. So this is a trick that you're going to see quite often in problems when there's a sum or a difference and one or both of those terms are radicals. The other thing I want to say is that in all of these problems, if we had in the original problem tried to plug in 0 for the variable, we would have ended up with 0 over 0. You can try it yourself if you want, but if you plug in 0 for t, you get 0 over 0. If you plug in 0 for h, you get 0 over 0. And in the previous video, the example that we looked at with x's, if you plugged in x equals 1, you got 0 over 0. And so all of these were limits that looked like they were approaching 0 over 0. Or if you were to direct substitute, you would get 0 over 0. But the limits that we ended up in the end, we had 2 in the previous problem, in the other video, and then 6 here, and then 0 here. And so the takeaway is that when we have something that's looking like 0 over 0, really the limit could be anything. And that's another reason why we have to be really careful when we've got 0 over 0, because there really are an infinite number of situations that we could end up in. And so we really have to examine each of those on a case-by-case basis, see what we can do with our algebra, our manipulations, our arithmetic, etc., to figure out exactly what's going on in that particular situation.